Hello everyone, welcome back. In our first video, we explored what dialysis actually is and how the dialysate fluid turns a simple filtration process into a life-saving therapy. Now let's take the next step and understand the core physics behind dialysis, which is the solute movement. When we bring a patient's blood into contact with the dialysate through a semi-permeable membrane, the entire exchange of toxins and water depends on how the solutes move. This right here is the foundation of dialysis physics. Before we discuss solute transfer, let's briefly look at the types of uremic toxins because how they move depends on their molecular size. Uremic toxins are broadly categorized into three categories. Number one, small molecules which weigh less than 500 daltons, and this includes molecules like urea, creatinine, etc. And then we have middle molecules weighing between 500 and 60,000 daltons, and this include molecules like vitamin B12, PTH, and advanced glycation introlex. And subsequently, we have protein-bound uremic toxins. These are actually small molecules but are chemically bound to albumin, which weighs around 60,000 daltons. Because of the tight bond, these protein-bound uremic toxins cannot cross the dialysis membrane freely. This difference in molecular size and protein binding determines how well each toxin is cleared during dialysis. So now let's talk about diffusion, the most fundamental mechanism of solute transport. Think about dipping a tea bag into a cup of hot water. The tea essence spreads out from inside the bag where its concentration is high to the outside water where the concentration is low. Look closely. The smaller molecules move quickly and spread throughout the cup, whereas the larger molecules move more slowly, and importantly, only solutes move. There's no net movement of water. That's exactly what happens in diffusion during dialysis. Solutes move from a higher concentration to a lower concentration, and the solute movement is limited by the pore size of the dialyzer membrane, just like the mesh of the tea bag. Now let's move to the second principle, convection. Imagine you are making a lemonade. You squeeze lemons into water, add sugar, and then pour the mixture through a filter. Here, the entire fluid, that is, the water, sugar, lemon pulp, and even the lemon seeds move together depending on how much you pour through the filter. If you pour just a little, only a small amount crosses over. If you pour the entire jar, a lot of solutes, both big and small, move along with it. This is convection or solvent drag. Solutes being carried by moving water. Unlike diffusion, here there is net water movement and the solutes travel along with it, limited only by the pore size of the filter. Let's imagine we have a semi-permeable membrane separating two compartments, one representing blood and the other dialysate. Now in the blood compartment, we have 10 small molecules, 10 middle molecules, 10 large protein-bound toxins, and 10 molecules of water. On the dialysate side, we have only water and no solutes. If we just keep both the compartments side by side for some time, the solutes start moving across the membrane. The small molecules like urea and creatinine are light and move rapidly through the membrane pores. So in a given time t, they distribute equally across both the compartments. The middle molecules like beta-2 microglobulin are larger in size. They can still pass through but more slowly. So they might take longer, say time 2t, to reach equilibrium. The large molecules like protein-bound toxins are much bigger and cannot cross the membrane pores easily, so they remain confined to the blood side. And finally, note that during diffusion, there is no net water movement, only solute exchange. So to summarize this part, diffusion occurs along a concentration gradient. Smaller molecules move faster than the larger ones. The membrane pore size limits solute movement, and then there is no net water movement in diffusion. Now let's move to the second mechanism, convection. Here, the principle is very different. Imagine the same setup again, 10 small, 10 middle, 10 large molecules, and 10 molecules of water on the blood side. But this time, a transmembrane pressure is applied to the blood compartment. This pressure pushes water across the membrane into the dialysate site. As water moves, it drags along solutes, mainly small and middle molecules, through the membrane pores. So let's say two molecules of water are filtered across. They carry along two small and two middle molecules. The larger molecules still remain behind, limited by the pore size. This is called solvent drag, where solute movement depends on the volume of fluid filtered and not on the molecular weight. So in convection, there is net water movement. Solutes move along with water. Solute clearance depends on convection volume, and again, the membrane pore size limits how big a molecule can cross. Now to simplify, diffusion is what we use in hemodialysis. Solutes move based on concentration difference. Convection is what we use in hemofiltration. Solutes move along with filtered fluid. You might now ask, if you are filtering fluid along with the toxins, won't the patient become dehydrated or hemoconcentrated? That's a great question. To avoid that, we use replacement fluid. which plays the role of dialysate in hemofiltration. Let's say we remove 10 liters of fluid from the patient. This fluid contains electrolytes in physiological concentrations plus waste products. We then replace it with 10 liters of a clean replacement solution, a fluid with the same electrolytes in physiological concentrations but without waste products. So essentially, you are removing dirty fluid and replacing it with clean fluid, achieving toxin removal while maintaining fluid balance. This is how hemofiltration clears toxins through convection while avoiding dehydration. Now let's see what drives convection. We can move fluid across the membrane using either hydrostatic pressure as in hemofiltration or osmotic pressure as in peritoneal dialysis using dextrose-based dialysate. In hemofiltration, a positive pressure is applied to the blood side relative to the dialysate side. This transmembrane pressure forces water and dissolved solutes to move across, and dialyzer membranes are classified based on their water permeability, and these are expressed as KUF, ultrafiltration coefficient, and this KUF depends on the membrane thickness and the membrane pore size. Low flex dialyzers usually have lower ultrafiltration coefficient, usually less than 10 milliliter of water transfer per hour per millimeter mercury of transmembrane pressure applied, whereas high flex dialyzers will have higher KUF, usually more than 20 ml per hour per millimeter mercury of TMP applied. Because of the smaller pore size, low flex dialyzers usually allow only the transfer of small solutes, whereas high flex dialyzers, owing to their larger pore size, allow both small and middle molecule transfer. However, even with high flex membranes, we can't efficiently clear protein-bound uremic toxins, because even if we increase the pore size, removing them would mean losing albumin, which is undesirable. Interestingly, even the natural kidneys don't remove protein-bound toxins by filtration. Instead, the renal tubules secrete them using specialized transporters like organic anion transporters. This mechanism lets the toxins move into urine without losing albumin. That is something dialysis can't yet replicate. But there are experimental methods being studied. For example, infusing fatty acids during dialysis. Fatty acids bind to albumin at the same site as protein-bound uremic toxins and can displace them, allowing some of these toxins to be cleared as free molecules. The principle of convection also applies in peritoneal dialysis, but here the driving force is osmotic pressure. The glucose in the dialysate draws water from the blood capillaries into the peritoneal cavity, and the moving fluid carries solute along with it, which is another form of solvent drag. So let's simplify it. Diffusion is solute movement based on concentration gradient used in hemodialysis. Convection is solute movement with water flow used in hemofiltration. When we combine both, that is hemodiafiltration, we get the best of both worlds, better clearance of both small and middle molecules. And when we remove small volumes of fluid for volume control, it is called ultrafiltration. When we remove and replace large volumes of fluid to normalize solutes, it is called hemofiltration. Essentially, both are convective processes, differing only in purpose and scale. So that's all about solute movement in dialysis, diffusion and convection, the twin principles that make blood purification possible. In the next video, we'll go deeper into effluent saturation, extraction ratio, and the concept of clearance, and we'll see how the blood flow, dialysate flow, and the membrane efficiency determine dialysis adequacy. Thanks for watching. Don't forget to like, share, and subscribe for the next episode in this Dialysis Simplified series.